Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, I would be now giving you an overview of advanced machining processes, and this is about how you make the micro structured systems or microsystems. So, let us just briefly review what we did in the last lecture. So, we had a historical perspective of microsystems. We went into some concepts and the way that the miniaturization drive had emerged, starting from the very famous lecture of Sir Richard Feynman in 1959. We talked about Moore's law and the integration density, and how Moore's law is increasingly changing from doubling in 18 months to doubling in about 24 months. We also talked at length about physical and biological MEMS, and discussed some very interesting examples of physical and biological MEMS systems. So, the take home message for this particular lecture was really that it is a synergistic learning experience with the biological world. So, there are a lot of inspirational material available from the biological world that can be translated to make microstructured systems, nanosystems. And so, therefore, a vast majority of fabrication processes are really bio inspired as well. So, we will do this in details while looking into a historical perspective of how parallelly machining or microstructuring evolved over time. So, let us get a historical perspective of some of these processes which are known as manufacturing processes. So, we have already in our engineering lectures prior to this seen that a lot of parts can be manufactured by some of these basic processes like casting, forming, and various shaping processes, and therefore, all these processes making parts really require further finishing before they are ready to be used in an assembled form. And these sort of high throughput processes are further required to be fine processed, so that whatever requirements of tolerances are dictated by engineering assemblies of such parts can be realized. And so, this is really one of the reasons why initially advanced manufacturing processes were developed, so that the tolerances up to the size of microns, or even nowadays increasingly to nanometers, can be easily provided by the advancement of the process itself. Sometimes also in many engineering applications, interchangeability of a part is a major issue, which needs these specific dimensional accuracy and surface finish. So, this again dictated the need for these advanced manufacturing processes. So, let us look at one of these processes, machining, which involves the removal of some material from a workpiece in order to produce a specific geometry, and that too at a certain degree of accuracy and surface quality. So, with a machining into picture, one can really look into the history of machining, or where this concept of shaping objects started. So, one of the first examples in the mankind of sort of machining comes from this most ancient Paleolithic stone tool industry, the old one. Okay. It was developed about 2.6 million years ago by members of the genus called Homo habilis or Homo sapiens, and they were really tools shaped out of stones as choppers, burins and awls, as some examples can be seen here. Okay. So, man really learned to remove material in a desirable manner as far back as the Paleolithic age. Further developments happened, and the invention of nets or bolas, where this big rock in a carved in a spherical manner would be tied up on a rope and thrown onto animals to make hunting possible, or even spears, which would be something like what you saw here, tied at the end of a big stick, or bow and arrows developed. Okay. So, interestingly, machining dates as far back as this period. Okay. And slowly things changed, and we went into the copper age, where still handheld tools had a lot of prominence in the copper as well as the bronze age, which was about 1,000,000 years back. So, some example problems are illustrated again here. This was a ceremonial giant dirk of found in France in the year 1500 and belongs to a year 1500 to 1300 BC. This was some Bronze Age weaponry and ornaments which were developed by people who learned some of the basic manufacturing processes by this time, and still everything was really manual or handheld. So, almost up to 17th century, all the tools which men used for developing some of these fine objects were hand operated, and the methods were very, very elementary up till a little bit later. Of course, humankind found out that the power of water or steam could be very easily used, and of course, much later it was realized that electricity could be again another very useful source of delivering energy, so that you could power drive some of the tools for creating different shapes onto metals. And so, if you look at one of the first illustrations, it comes from this John Wilkinson in 1774, who first constructed a precision machine for boring engine cylinders, and it was powered by steam. So, this is one of the earliest examples of how machining could actually take place and increasingly go into the powered domain from the manual domain. This followed a lot of other illustrations later on. For example, 23 years later, Henry Maudslay actually developed this screw cutting lathe, as is illustrated in this particular example here. Okay. And then of course, James Naismith invented the second basic machining tool for shaping and planing, which is again illustrated in this particular figure here. Okay. And then the first universal milling machine was built by J.R. Brown in the year 1862, and these were all power tools, starting with John Wilkinson's first engine boring system, which used the steam for providing the power. So, after these basic machining tools were developed to have high throughput processes or highly productive processes, people realized that finishing was a very important aspect, and so in the late 19th century, the grinding machine was introduced for the first time, and as a more advanced form, this process later on changed to lapping, and high quality surface finishes with very tight tolerances could be easily realized using a combination of grinding and lapping processes on the primary machining operations, which were done by these powered systems, as we illustrated before. So, if we look into a little more of history, in the later part of these 19th and 20th centuries, machine tools first became increasingly electrically powered. Okay. And they had many refinements. For example, people shifted from single cutters to multiple point cutters, and milling tool was introduced for the first time based on this concept. the whole machining paradigm, although it was powered, was still dependent on operators and human skill, who by their own judgment would look at parts and use his or her skills to completely provide the sequence of operations, and therefore the workpiece accuracy would typically depend on the operator. So, as an increasing need for precision was felt rapidly in the industry, particularly because of complex systems like automotives, etc., which emerged on a commercial scale during this time. For the first time in 1953, the introduction to numerical control systems, where a computer's power would be used with a numerical logic for obtaining a good precision and repeatability of relative motion between a tool and a workpiece was felt. And so, with all these capabilities integrated together, the present capability of these tooling systems have really enormously increased up to the level of initially it was about a micron, but then with the current technologies of chemical, photochemical, and some high energy beam based machining, it can go to the size range of a few atoms. So, it is about probably tens of nanometers that this limit has been pushed to increasingly. And not only that, it has tremendous capabilities of producing complex shapes with the kind of finishing accuracies which can be as low as let us say a micron level finish. So, increasingly the power of machining industry has grown over the various decades, and up till now this power can be really manipulated and maneuvered to even place a few atoms and molecules, and so that is what the accuracy level has slowly gone into. So, in modern machining practices, of course, one important aspect is to be able to remove material which is harder, stronger and tougher, and it is more difficult to cut, and that is one of the goals of some of these modern machining practices. And it should be independent of so the cutting processes should really be independent of material properties of the workpiece, and as such increasingly from this so called conventional domain of metal to metal cutting, increasingly the focus has changed into some of these non-conventional machining practices, which has become very, very handy as an alternative, particularly if you have to realize complex shapes with a certain amount of surface integrity, and most important aspect, miniaturization or micron size requirements of the components. So, in this course typically we would be more focused on to this non-conventional machining domain and the way that it would be used for creating some of or achieving some of these targets, as machining complex shapes or going very, very small teeny tiny components, how that can be manufactured. Would be probably going through some material based on that. Okay. Of course, needless to mention is this concept of hybrid machining, which combines the enhanced advantages of more than two processes, okay, two or more than two processes, so that your objective of super high finish and high productivity, or maybe super high finish and complex shape, both can be achieved together. So, because of all these domains which are now increasingly available in machining science, micro machining has emerged into a domain where really very small, up to about 1 micron or so feature sizes can be realized very easily, combining some of these technologies as hybrid machining technologies. So, recent applications of micro machining could include silicon and glass micro machining, excimer laser based machining, photolithography, and these are some of the most modern processes of non-conventional machining. which is used this particular domain. Okay, so machining has increasingly also come up from precision grinders, where an accuracy of about plus minus 1 microns can be measured using some non-contact mediated measurement processes like interferometry or laser based instruments. And the future trends in micro machining really includes the power of beams of either photons or particles, and processes like electron beam lithography or focused ion beam is increasingly being used to realize or micro manipulate materials even down to the atomic level in a very precise manner. So, these combined with a few other processes also are classified into the area of nano machining as a very recent trend, and these processes are capable of manipulation at the atomic and the molecular level. And the nano machining concept really was first introduced by Taniguchi, and it covered miniaturization of components and tolerances in the range of submicron level, and also to the level of hundreds of nanometers or even as low as 0.1 nanometers in the various domains that was proposed by Taniguchi in his model for nano machining. So, let us look at some of the machining accuracies with respect to the number of years, as can be illustrated here in figure 1.1. And as you can see, these different domains of machining, like for example turning and milling machines, grinding CNC machining centers, lapping, honing, jig boring and grinding, so on and so forth. So, these are the different equipments and machine tool classes which are grouped together in order of how much machining accuracies they can produce. And if you look at the way that this machining has evolved or is evolved from as far back as 1940 to the late 2000, you can see that the machining accuracy really has changed quite a bit, from about, let us say 0.1 inches to hundreds of microns to about close to as low as about 1 micron, particularly if you were to take into account these three conventional domain processes: turning, milling, grinding, CNC milling centers, lapping, honing, jig boring and grinding, so on and so forth. So, this also is the normal machining domain, and so you can achieve up to a machining accuracy of 1 microns by the year 2000, as you can see here, and this has really been achieved as indicated in this particular chart. Some of the other processes like precision grinding, super finishing, diamond grinding and turning, high precision mask aligners, ultra precision diamond turnings, they come in the domain of precision machining. Okay, and here the machining accuracy really starts from about 1 micron and goes down further to almost about hundreds of nanometers, about 0.01 microns, and that could be roughly about 10 to the power of minus 6th of an inch. If you go a little further down here, the electron beam soft X-ray lithography, ion beam machining, molecular beam epitaxy, ion implementation, and we will understand some of the basic machining principles and processes as we move along. They can be classed into this ultra precision machining domain, where the machining accuracy is as low as hundreds of nanometers of 0.1 microns is the starting line, and it goes all the way to about 0.001 microns, which is about 1 nanometer, which is that of even atomic manipulation, at the level of lattice separation, etc. So, you can see that with increasing time varying from 1940 to 2000, the machining paradigm, classified normally as a normal domain, precision domain and ultra precision domain, have gone from all the way from about hundreds of microns to as low as about 1 nanometer, which is that of simple lattice spacing between the atoms. So, such is the power of machining technology and its emergence over the number of years. So, let us actually now look at a broad classification of all the machining or the material removal processes. And here I would like to classify the processes as a traditional domain and then the non-traditional or non-conventional domain. And of course, this would be our area of interest for this particular course, although a brief mention would be made of the traditional domain processes. So, in the traditional machining area, if you look at the class and the subclasses of these machining, you have a category of cutting processes where these different processes can be classed as turning, boring, drilling. These are all cutting processes, and this would be able to generate circular shapes, and then some other shapes can also be generated by these other set of cutting processes or metal cutting mechanisms like milling, planing, shaping, broaching, sawing, filing, gear forming, gear generating, so on and so forth. So, traditional machining has this one class or one domain where you are actually having a metal to metal cutting, and then there is another domain which is used for finish machining operations on this cut pieces, which is mechanical abrasion based, and then it can be based on bonded abrasives like you often find in grinding or honing or coated abrasives technology, or loose abrasives that you often find in polishing or buffing, right, where the slurry really contains the abrasive and then the polisher or the tool is really rubbing the slurry against the workpiece surface. So, therefore, that is how traditional machining domain can be classed, and of course, needless to say is that this is a high throughput, low accuracy process, and the mechanical abrasion is actually a relatively lower yield, but high accuracy process as far as the traditional machining domain is concerned. So, we have already made a case before to illustrate that these traditional domain processes may not be that useful when you come to realize or machine increasingly tougher or high strength materials with complex shapes and precision or accuracy up to the level of even atomic manipulation. And so, therefore, these set of machining parameters called the non-traditional machining techniques come into picture, and they typically include chemical machining, electrochemical machining, electrochemical grinding, electrodischarge machining, laser beam machining, abrasive jet machining, water jet machining, plasma beam machining, and ultrasonic machining. So, these are some of the different illustrations of the machining domain, where very small surface finishes or even micro feature sizes can be increasingly found. And then there is a whole domain of silicon machining, which also is borrowed from the microelectronic processing industry, which we would be looking at in great details. So, let us look into some briefly into the conventional domain of the machining before starting. And so, typically in the conventional domain, as we all realize that there is a tool, and this tool is used for penetrating work material to remove certain amount of material up to a depth, okay, and the amount of depth that the tool goes into the material is also known as the depth of cut. So, there is of course a relative motion between the tool and the workpiece, and different geometries can be realized based on this relative motion between the tool and the workpiece. For example, look at turning, the way it produces cylindrical parts. So, you have a single point cutting tool, and there is a mass which needs to be machined, and it is rotated at a certain RPM, and the tool goes and scribes off the material and increasingly goes deeper and deeper into the material, so that the circular symmetry of cut can be generated and a cylindrical piece can be generated based on that. Of course, there are shaping and milling which generates flat surfaces. Then there are drilling processes where you can produce holes up to any dimensions of different diameters, where again the relative motion between the tool, in this case the tool rotates and the workpiece is fed linearly. It determines really how the shape of machining is going to be on the workpiece. So, because of this regular scribing of material, there is a temperature generated at the machining zone, and that is advantageous for high productivity and better finish, primarily because there is a slight reduction in the strength and the ductility of the material that you are cutting, and the preheating always helps to make the material softer, and so you can at a very high yield and better finishing accuracies be able to cut materials. So, there are certain illustrations found in literature, for example, a paper by El-Kadi et al., as you can see here in 1998, which claimed for the first time that formation of a continuous chip from discontinuous ones were due to workpiece heating. And then of course, this Torr and Copley 1997 who actually built a laser assisted prototype to improve the machinability of difficult to cut materials on traditional turning processes by preheating using this laser assisted system. Okay. So, it was focused the laser beam onto the workpiece just above the machining zone and reduced the cutting forces by quite a bit and improved also the tool performance this way. So, some examples where playing around with the temperature of the material in order to get better finishes or more amount of material removal have already been demonstrated by various people using conventional machining domain. So, if you categorize the different metal cutting processes, they can be either categorized into the forming processes or the generation processes, and I would like to classify between the two. So, a forming process typically is when a cutting tool possesses the finished contour of the workpiece. For example, let us say for example, in this illustration, this tool here is having a inverted contour, okay, as can be illustrated here, of whatever it produces finally onto the workpiece surface. And so, you give it a feed and then also give it a cutting motion, and whatever contour is there on the surface of this tool is replicated in negative form onto the surface of the workpiece over which this is moving. So, you are forming the shape which was there on the tool, the negative of the shape which was there on the tool over the workpiece surface. So, it is called forming. Okay. A surface may incidentally also be generated. For example, let us say this single point cutting tool example in a lathe, where there is a movement of rotation given to the workpiece, and the tool is fed in this particular direction and also given a depth of cut, so that there is a circular symmetry which is developed of the cutting zone, resulting in development of a different shape. So, these processes can be thought of as generating the contour or the feature by relative motion of the tool with respect to the workpiece. There can be a combination of both the forming and generation processes, as can be illustrated in this particular example, which is a slot milling example, where the forming can be thought of as provided by the thickness of this cutter, and the milling can be thought of as a relative motion between the tool and the workpiece doing the machining operation. So, another process, so these are all the metal cutting processes, and the other processes that I was referring to is based on machining by abrasion. And in abrasion machining, the machining allowance is removed by a multitude of hard angular abrasive particles or grains, which we also know as grits, and which may or may not be bonded to form a tool of definite geometry. So, in contrast to the metal cutting processes during abrasive machining, the individual cutting edges are randomly oriented, and the depth of engagement is small and not equal for all the abrasive grains. There is an averaging effect of the cutting depth, which results in a sort of surface finish on the high yield processes, like some of these metal cutting processes, forming or generation processes, etc. So, it is really a finish machining operation, and not all the abrasive grains are simultaneously able to remove. So, they come in contact one by one, and then they remove their own material by brittle fracture, and therefore, the averaging effect also becomes more prominent, because the chips removed are very minute, and most of them are invisible, because the temperature of operation is so high that they get oxidized, and you can see a flame come out from the such abrasion or such rubbing action of the abrasive. So, let us look at some of the schematics of how abrasion happens. So, typically one very interesting abrasion process is, of course, mechanical grinding, and, and then some of the other processes are honing and super finishing processes that employ either a solid grinding wheel or sticks in the form of bonded abrasive. So, this is illustrated here in this example, where you can see that there is a stick. For example, this is the honing process, and this stick here illustrated by this highlighted region, okay, is containing the abrasive grains or the grits adhesively or bonded onto the surface by using an adhesive, and you apply a low pressure to this honing stick and move this stick with respect to the workpiece. So, there is a gradual finishing of the workpiece surface, and you can use as a medium something like oil, which carries off the material which is dislodged from the workpiece because of this low pressure of the honing stick. Another interesting example of metal abrasion process is where, instead of the adhesive being bonded, as was the case earlier with grinding or honing, the adhesives are open, and you use a wheel to rub the adhesive, which is typically in the slurry. So, this slurry which is around this region really contains the adhesive or abrasive, I am sorry, the slurry contains the abrasive particles, okay, and the tool here is nothing but a rubbing agent, where it takes the abrasive slurry and rubs against the workpiece, and the tool can be rotary in nature, as you can see here, and these are used for very soft applications, like for example, when really high level of finishing like polishing operations are needed, you can use some of these techniques like lapping or buffing or polishing, where loose abrasives are used in a liquid media, and the tool as such is nothing but a rubbing agent of these loose abrasive particles. So, that is how abrasive machining can be categorized into various different domains. Now, let us get into the domain of the non-traditional machining processes, as we have illustrated so far many times. So, traditional machining, of course, is as you know, mostly based on removal of materials using tools that are harder than the materials themselves, and increasingly the need for non-traditional is really felt because of the novel materials or alloys or high strength composites which are being developed by material science, so that these techniques can be commensurate with such novel materials, which are increasingly finding engineering applications in even industries. So, what are those non-traditional processes, or what is the domain of the non-traditional machining? So, we can actually have a closer look by going into this particular illustration or slide. Okay. So, here I have tried to classify some of these non-traditional or advanced manufacturing processes into different domains, and there are three principal domains that we can really classify these non-traditional machining processes as. There is a mechanical machining domain where you can again use mechanical removal of material as a means of doing machining. Of course, in this particular case, as you will see, the material removal will not be in a bulk state as turning or grinding processes, but in a very superfine state by use of abrasive materials in a very interesting manner. There are thermal ways and means of removing a material. For example, what an electric discharge can do, or a power of an electric beam can be used for machining or material removal, or as a matter of fact, power of laser beam or ion beam or plasma beam can be increasingly used for some of these thermal processes. And then of course, there are this chemical and electrochemical machining processes where things like lithography, or even where the power of a chemical called photoresist to be able to microstructure itself very accurately can be used for going smaller and do micro manufacturing with high surface finish and micro components, micro systems as such, so on and so forth. Then of course, there is this ECM or electrochemical machining, where particularly metallic domain materials in the metallic domain can be easily removed using ECM, where complex shapes in the most intricate corners can be machined very easily. And then of course, there is a huge domain of photochemical machining, which can be a combination between optics and chemical machining. So therefore, the most of the non-traditional processes are classified only into these three kinds: mechanical, thermal and chemical or electrochemical means of removal. And it is not necessary that only one process can be used. You can use hybrid processes where you can have the combination of more than one process. And by the by, this classification is really based on how you are applying the energy. So you can actually have the machining action using mechanical energy or thermal energy or chemical or electrochemical energy, and they form the classification basis of these different material removal processes in the non-traditional domain. Let us look at these machining processes one by one. So the first mechanical machining process which comes to our mind is ultrasonic machining, or as a matter of fact, water jet machining, which are typical examples of single action mechanical non-traditional machining processes. So if you look at the schematically how this happens, is that there is a mixture of abrasive grains. Okay, so this mixture can be made up of a medium, a liquid medium, into which these grains are immersed, and these grains are all individually capable of moving and free to move. And this grain containing slurry is pressed onto a workpiece by means of a tool which vibrates at ultrasonic frequency. So essentially, this tool head which vibrates, let us say in this direction, in the positive z direction, at some above sonic frequency or ultrasonic frequency, is able to hit the abrasive grain onto the workpiece surface and thus remove material in the brittle fracture mode. Okay, and so super finishing processes again sometimes use these USM driven material removal mechanism, where the feed or the depth of cut or even the tool frequency can be adjusted in a manner so that different levels of finishes can be obtained on the surface. For example, another example of a mechanical machining process is what you can do with water jet machining. So essentially here, as the name sounds, there is a jet of water which is released at a high pressure, and there is a forced directed small jet area which is used to cut the workpiece. Sometimes you have abrasives loading this water jet, and so you will have the process slightly modified from WJM to AWJM, abrasive water jet machining. So therefore, use an abrasive material to actually perform the cutting action here, and the jet provides the impact to the abrasive material to cause the brittle fracture. So the machining medium in most of these cases are solid grains suspended in cutting fluids, and you can actually replace the abrasive grain by ice particles, and so that can subsequently be called as ice jet machining. So all these are mechanical non-traditional processes, because the action that is applied here is really brittle fracture based mechanics of removal of the material, and therefore mechanical. So we will look into the details of this process, particularly the USM and the abrasive jet machining processes a little bit later. And let's come to the second modality of material removal, which is also known as thermal machining operation. So here really the modality is thermal, in the sense that you are trying to apply heat energy so that it can cause melting or vaporization of the workpiece material, thereby removing the material as liquid or vapor state. So there are many secondary phenomena, of course, which occur when thermal machining is being considered. For example, micro cracking, formation of heat affected zones, striations or banding phenomena, which can come during the thermal machining processes if they are not very well controlled. And so therefore an important modeling aspect of such processes come into picture, which we will look into great details as we go over some of these processes. So the source of heat could either in this case be that of an electric discharge, as you can see here in EDM. So there is a plasma or a discharge which is created between the workpiece and the electrode, and the dielectric material inside in between the workpiece and the electrode acts as an insulator really, where the plasma can be created in specific columns. And so whenever this plasma gets created, the electron pressure is able to create a local temperature enhancement, so thus taking the material, the workpiece material, to wherever this plasma strikes to its melting point, and whatever melt is withdrawn is removed by this circulating dielectric material. So this is one form of machining called electrodischarge machining. The power of the thermal power can be provided by a plasma beam, and that then would be called plasma beam machining, or let us say an electron beam. So therefore that can be called as e-beam machining or electron beam machining, or it can be any other form like an ion beam or a laser beam. And the mechanics of removal of the material here is more or less thermal, but the conversion principles are different. For example, in electrons it is really the kinetic energy exchange between the penetrating electron and the lattice of the material, whereas in laser beam machining it is a photon to phonon conversion or the conversion of photons into bond vibrations, which results in the machining process. And so thermal machining also is increasingly being performed in hybrid machining processes, where some of these conventional formulated micro parts are given a secondary treatment using some of these thermal machining processes for issues like complex geometries or even good surface finishes, etc. A third category of processes is the chemical and the electrochemical machining processes, as is illustrated here. In the electrochemical machining process, you again have an electrode and workpiece as another electrode, and the electrolyte is flown in between the workpiece and the electrode in question, and therefore there is always an ion transport which happens in between the electrolyte, where material is removed from the workpiece, and the idea is that it should not get deposited onto the electrode, but should get precipitated as soon as it gets removed from the workpiece. So, the electrolyte constitution is very critical, so that it is not only able to create an ion movement from the workpiece, but also is able to precipitate the material and move the material if we can circulate the electrolyte around. And so, that is what is meant by electrochemical machining, and it is governed by Faraday's principles, and you can really calculate and model the electrochemical machining rate based on some of these basic physics principles. The other process is chemical or a photochemical machining process, where again chemical machining would formulate the domain of etching, where etching is really nothing but sort of engraving of metal structure, or engraving of a certain area of a metal or any other substrate by etching it selectively with respect to a chemical. So, that chemical can cause either a redox reaction on the surface, or it can actually make a state of atoms removed from the surface which cannot dissolve very well, and it gets increasingly carried away. It can also be a gas based system, where the same etching action is provided by a gas and not a liquid chemical. And so, therefore, some of these processes increasingly used in silicon micromachining, like PECVD, plasma enhanced chemical vapor deposition, or CVD, chemical vapor deposition, can be used increasingly to either bulk micromachine or surface micromachine some of these microsystems. Photochemical machining again is a very wide area of interest as far as the microsystems machining goes, and this photochemical machining typically includes a photographic film called resist, and this resist is removed selectively with respect to a mask and selective exposure to a certain frequency light. So, therefore, if you can formulate a coat of this resist and selectively remove materials off its surface, then those can result in vias and trenches, which can expose the substrate, the parent substrate, selectively for chemical machining and other different forms of machining. So, photochemical machining certainly is a very important area as far as the microsystems fabrication technology goes, and we will actually look into the details of some of these systems later. So, thus this chemical machining may include the domain of chemical milling, photochemical blanking, chemical dissolution, and basically such actions are again used to remove the machining allowance through ions in an etchant. Okay, and electrochemical machining of course uses electrochemical dissolution by the passage of electrons and ions from within the electrolyte, and those machining allowances can be removed, or the material can be removed to formulate the machining allowance using an ion transfer mechanism in a electrolytic cell. So, that in a nutshell is what is a brief description of what would be in the course content. So, on one hand, we are actually going to learn this fabricating of microsystems with an angle of micro manufacturing, and on another hand, and so this would mostly include silicon based processes, processes which can be increasingly applied to polymeric systems or glasses, okay, from a standpoint of microsystems fabrication. And then the other end of the course would actually delve into these advanced machining technologies which have been indicated here, that is thermal, mechanical and chemical, electrochemical forms of machinings. And then finally, we would like to integrate number 1 with number 2, okay, so that we can use these advanced machining or non-traditional machining processes for making manufacturing microsystems. Okay, and so this section of the course would be dedicated to mostly some of the advanced research articles which would focus on how MEMS can be created using non-conventional machining technologies. And then we would also like to demonstrate practically some of the microsystems fabrication protocols and processes where non-traditional machining is actually realized, is actually used in practice to formulate a real microsystem. So that's in a nutshell what this course is intended to be.